Welcome to the development lesson on Montana Early Warning System. In this video, we will show how the early warning system was developed from the data of Montana students. Also, this video will detail the data variables that have been researched and which ones are actually in the EWS models. If you have any questions or concerns about the Montana Early Warning System, please contact Eric Meredith. The Montana EWS is a statistical model that uses readily available school, student, and other live data to identify students who are at risk of dropping out of school. The goal is to identify these students as early as possible in their schooling to allow educators to have an opportunity to intervene and help the student graduate. The earlier a student can be identified at risk, the better their likelihood of becoming a graduate versus a dropout. In this lesson, we are going to cover how the statistical model behind the EWS was developed. This is only a small snapshot of information about how the EWS was developed. If you are interested in more in-depth analysis, please contact OPI. First, we need to determine what data is available to include in the early warning system. The OPI collects data about each public school student in grades K-12 throughout the state. Most of that data is contained in the Student Information System that Montana uses from Infinite Campus. This data includes age, grade, school attended, programs the student participated in, demographic information, and other data. The OPI also has testing results from the statewide assessment. This test was the CRT. However, the Smarter Balance test is now used. There is also data available on the individual schools. This includes things such as school size, school location, the percent of American Indian students in the school, and other data. Along with the school and student data, there is also data available through the census that includes town population, poverty rates, unemployment rates, and more. The second block of data is data that is collected and stored by the schools. This is data that OPI does not collect on a statewide basis. This data includes daily attendance, grades, and behavior data. Research has shown that some of this data is the most relevant when building an early warning system. So to include this data, the OPI was granted access by several schools throughout the state for the sole purpose of building an early warning system. All total, about 300 variables have been analyzed for inclusion in the early warning system, and that number is always increasing. One of the first steps of building an early warning system is creating the historical data set from the model that will be derived from. This being an EWS for Montana, the data must come from Montana students. This data set includes students from 2007 through 2016 school years for students that have either graduated or dropped out. As explained before, the OPI does not collect some important data needed to be included in the EWS. So 13 school systems, which are essentially towns, granted the OPI access to their student information systems, and the attendance, discipline, and grades data the OPI does not collect. These 13 school systems include roughly 11,000 students per year, or about 1/6 of the statewide student population in grades 6 through 12. This encompasses the sample data set that EWS will be based on. These 13 school systems vary widely in size, school demographics, location, and other attributes that make them a good sample for the state of Montana. The data is then set up so that only one enrollment for each student is included per year. This enrollment is always the last enrollment of the school year for each student. Once the data set is compiled, the idea is to basically compare dropouts to graduates in the data set. What characteristics make up a graduate and what constitutes a dropout? The analysis itself is a bit more complicated, but that is essentially what the analysis is doing. The Montana Early Warning System uses a model that utilizes logistic regression. The equation presented may look a bit scary, but really is not. Each x is a variable, such as attendance rate, and the corresponding beta is the coefficient or weight applied to that variable. Some variables are more important than others, so they are given a stronger weight. The important part to know is that the end result of the equation, pi of x, is the percent chance a student will drop out of school based on their data. Each grade has its own model. This is for many reasons. One is certain variables aren't available at all grades, such as the number of credits earned towards graduation. Students not yet in high school would always have 0, so creating one equation for all students wouldn't work. Another reason is at different grades, different variables have greater effect. For example, behavior during 12th grade year is not as big a factor as it is for 8th grade students. Also, when I say each grade has a separate model, for high school the models are not actually done by the grade assigned to the student. The models in high school are based on how many years the student has been in high school. So a student in their third year of high school has a separate model compared to a student in their second year. What grade the student is assigned, such as junior or 11th grade, doesn't matter. This slide shows the variables that have been included in the Montana early warning system. This list is what remains after 300 or so variables have been analyzed. Every variable is not included in every model. There are 6 variables that the OPI collects for all public school students statewide, and another 9 that is not collected by the OPI. These variables include information about the student for mobility, attendance, behavior, grades, and others. A little clarification on a couple of these variables. The age difference variable basically asks, is the student older for their grade than what they should be? It does not matter why the student is older, just whether or not they are. All variables with Y or N after it are yes or no binary data. On track is one of these variables and is based on the number of credits a student has earned. It tracks if a student is on track to graduate based on credits earned. So, for example, if a student starting his third year of high school, remember the student has completed 2 years of high school, has earned 14 credits, that means he's averaging 7 credits per year. If the school this student attends requires 24 credits to graduate, then over 4 years that student must average 6 credits per year. Since the student is averaging more than he is on track to graduate, this variable does not take into effect which classes the credits come from, just the number of credits earned. The other variables are self-explanatory. So now that we have a model built, the next question is, how do we know the model is doing as intended? There are 2 parts to a good early warning system model. The first is the model should assign a high dropout percentage to students who eventually end up dropping out, and therefore a low dropout percentage to those that eventually graduate. There are many ways this can be evaluated, including using the R-squared, C-statistics, and ROC curves and others. The second part to a good EWS model is the model should be efficient in identifying dropouts above some cutoff threshold for targeting a student at risk. Basically, what this means is a high percentage of students that are targeted by the EWS should end up dropping out. For example, if we target all students that have a dropout percentage above 50%, is that efficient in identifying the students we are trying to identify? This part can be evaluated by a confusion matrix. We want to identify as many dropouts as possible, right? Well, we could identify all of them if we just identify every student as at risk. But is that useful to a school? No. The idea here is to identify only the students that are at risk so we can focus on those students and use our resources to keep those students in school. A confusion matrix has 4 possible outcomes as shown in the slide. For example, a true negative results means the model indicated the student would graduate and the student did, in fact, graduate, which would be a good result. The model got it correct. A false negative results would be when the model says the student will graduate, but the student actually ends up dropping out. This means the model did not get it correct for the student. When evaluating the model, the boxes in black font are good outcomes, and that the model got the student correct, and the results in red font are bad outcomes, and that the model got the student incorrect. One thing to keep in mind here is that the errors are not equal. A false positive results means the model shows the student would drop out, but in fact the student ends up graduating. This is an error we can live with. It's still an error on the part of the model, but we can live with this one. The false negative results are the ones we want to minimize. These students are the ones the model is not identifying, but eventually drop out. So we want the false negative results to be at a minimum. So, as an example, let's compare a confusion matrix when any student that has a dropout percentage above 15% is identified as at risk. For a full data set, we need to allow time for the 6th grade students to graduate, which means we have to go back to the data as it would have looked at the beginning of the school year in 2009 and 2010. Using that data, we can run the EWS using the current model and see how the results would turn out in the confusion matrix. In that group of students the OPI has data for, there were 4,167 students, 512 of which eventually dropped out. The results of the confusion matrix are shown in the slide. You can see that the most students are in one of the boxes with black font that the model displayed correct results for. Also, it's important to note that the false negative box, the area we especially want to stay away from, is the smallest by far. Overall, about 75% of the dropouts were found in an overall accuracy of about 85%. These numbers are good. However, if a school actually used the EWS, the actual results in practice would be even better. This is for two reasons. One is that the data the OPI has found, schools have gotten much better at collecting accurate data since 2010. But the main reason is that these results are based on one snapshot, one result in time before the school year started in 2009. So for the 6th grade students, you are using that one result for the rest of their schooling until they graduate. In using the EWS in actual practice, you would have many results over each year even. This allows the model to update depending on how the student is doing and track them over time. A ROC curve is another way of evaluating a logistic regression model. The description of what is being graphed by a ROC curve is rather complicated, but basically every point along the line is measuring the confusion matrix in the past two slides of different cutoff values for identifying students as at risk. The location of the cutoff values for 0.75, 0.4, and 0.15 are shown on the graph. A point in the far upper left corner of the graph near the 1.0 would mean the model is perfect in identification. So we want that point that is closest to that upper left corner. As you can see, the 0.15 or 15% cutoff is one of the closest points. Using this analysis and others, it was decided that 15% is the best cutoff for identifying a student as at risk. So any student that the model assigns as having a 15% or higher chance of dropping out is at risk. Also, in the lower left of the graph is the C statistic, which is 0.8875. The C statistic denotes the probability the model will assign a higher dropout percentage to a randomly chosen dropout than to a randomly chosen student who eventually graduates. Any model with a C statistic above 0.8 is considered excellent in statistics. This slide shows two graphs that show more information about the EWS models. The combination of these two graphs is what's being graphed in the ROC curve in the previous slide. The slide on the left shows the percent of dropouts being identified. So, for example, if we make the cutoff be 0% and identify every student, then we will identify all the dropouts. But as explained earlier, this is not useful to schools. The graph on the right side shows the percentage of identified students that eventually drop out. The higher we make the cutoff, the higher percentage of students that end up dropping out. However, the higher we make that cutoff, the more students we will miss. So we have to take the information from both of these graphs and make a decision about what the cutoff value, which is what the ROC curve does. Another important cutoff is at 40%. If you look at the graph on the right, you will see that we use a cutoff value of 40%. About 2/3 of the students identified eventually drop out. The Montana EWS uses 15% as the cutoff for at risk, and any student that is higher than 40% is considered extreme risk. These graphs are displayed to show that these numbers were not just picked out of a hat and have statistical analysis behind them. The previous model diagnostics presented the results of all the models combined. This slide shows some model diagnostics for each individual model. R-squared is a popular way to measure the fit of a model, especially in linear regression. The R-squared presented here for logistic regression has a slightly different definition, but is similar. A perfect model would have an R-squared of 1. The C statistics are also presented here for each model. As mentioned before, a C statistic above 0.8 is considered excellent in statistics. One thing you will notice is the models for the younger grades are not as accurate for the older students. There are many reasons for this, but the biggest one is for a 6th grade student, you're trying to predict 6 years into the future. So there's going to be more variability in the results than there will be for a 12th grade student. While these model diagnostics are all acceptable, the OPI is working every summer to improve the models for better results and efficiency. That concludes this lesson on the development of the Montana Early Warning System. This slide shows the remaining lessons, including the next one in the series, Protecting Student Confidentiality.